Hello students, welcome back to a new video lecture on quantum mechanics. So in last videos we have seen about Schrodinger wave equation. So in this video lecture we will see what exactly eigenfunctions, eigenvalues, etc. So in order to solve whatever Schrodinger wave equation you got, so you have to solve that to find out the wave function psi. To find out the wave function psi, Schrodinger wave equation has to be solved. But you have seen it is a second order wave equation, second order differential equation. Second order differential equation. There are several solutions. But all them may not be correct wave function which we are searching for. So we have to select only those wave functions which are physical meaning and are called acceptable wave function. So those who have physical meaning, then they are called as acceptable wave function. These acceptable wave functions are called as eigenfunction. So acceptable wave function, that is those wave functions have physical meaning. They are known as acceptable wave function. So they are called as eigenfunction. So eigenfunction are those wave function of quantum mechanics which possesses following property. Eigenfunction should have the following property. Eigenfunction have following property, that is the wave function psi must be continuous. Of course, this is a property of wave function. Obviously, that should be satisfied. And finite, single valued, everywhere. That's the first property. Second property, of course, its first derivative, that is I am talking about partial derivative, dou psi by dou x, dou psi by dou y, and dou psi by dou z must also continuous, be continuous, and finite, single valued. Again, single valued. Okay, so if wave function satisfy these properties, then wave function are called as eigenfunction. So then what is eigenvalues? Next, let us see eigenvalues. So eigenvalues of energy, the values of energy for which Schrodinger wave equation can be solved are called as eigenvalues. Values of energy for which the Schrodinger wave equation can be solved is called as eigenvalues. So the wave function which satisfies certain properties are called as, or acceptable wave functions are called as eigenfunction. The values for which Schrodinger wave equation can be solved are called as eigenvalues. Let us see the application of Schrodinger wave equation. Say application of Schrodinger wave equation. So that application we are looking for is particle in one-dimensional particle in one-dimensional potential well of infinite height. That's very important. Infinite height. So there are, of course, it's also known as particle in a box. The infinite potential. So what we will do is let us consider a particle in a box. So let us say particle is confined. Of course, x is equal to 0. The width of the potential well, say let us say A is the width of the potential well, and inside the potential well, particle is having potential 0, V is equal to 0, and at the boundary it is having infinite potential. So infinite potential, V is equal to infinity, V is equal to infinity outside the potential well. So let us say particle is under the motion, moves along x direction, x axis, between x is equal to 0 and x is equal to A. That's the first thing. Second, the particle is free particle, that is not subjected to any force, external force. Therefore, potential energy is equal to 0. Particle is not subjected to any external force, therefore potential energy of the particle inside the box, that's whatever I am talking, between x is equal to 0 and x is equal to A. So V is equal to 0, that is between 0 and A. Okay. So it is having 0 potential because it is not subjected to any external force. But V is equal to infinity, that is outside the box, even when x is equal to 0 also it is infinity. X is equal to E. How you can write is x is less than or equal to 0, x is greater than or equal to A, so V is equal to infinity, which means particle cannot be found outside the box. You cannot find any particle outside the box because infinite potential, it's not possible. So let us try to write the Schrodinger equation for the particle inside the box. Inside the box can be written as d square psi by dx square plus 8 pi square m divided by h square E minus V. V is 0, so therefore you are left with E psi, that is equal to 0 because V is equal to 0 inside. Okay, so call this a 1. Let us consider, let 8 pi square m into E divided by h square, that let us consider it as k square. Let us assume that it's k square. So therefore the above equation reduces to d square psi by dx square plus k square psi is equal to 0 because 8 pi square m into E divided by square is taken as k square. So this is a second order differential equation. The solution of this equation is given by second order differential equation written as A psi kx plus b cos kx, where A and B are constants. So to evaluate A and B, we have to apply the boundary condition. Let us apply the boundary condition to evaluate constants. So At first, let us consider at x is equal to 0. At x is equal to 0, what is wave function? Wave function is equal to 0 because when x is equal to 0, potential goes to infinity. Potential goes to infinity. So therefore, probability of finding particle is 0. So therefore, wave function doesn't exist. Psi is equal to 0. So therefore, equation 4 becomes above equation psi becomes. So this psi is equal to 0. So 0 is equal to a sin kx plus b cos kx. So of course x is equal to 0. So therefore this becomes sin 0 cos 0 cos 0. So cos 0 is equal to 1, sin 0 is equal to 0. Therefore, b is equal to 0. First, we have evaluated first constant. Because sin 0, so therefore this vanishes. This term vanishes. So you are left with b cos 0, that is 1. So therefore you are left with 1. 1 is b is equal to 0. That's the first evaluation of the first constant. So next we have to evaluate second constant. Let us put the second boundary condition. What is the second boundary condition? That is at x is equal to a. Again psi is equal to 0. Psi is 0 because potential is infinite. So therefore equation 4 becomes 0 is equal to a sin ka. X is equal to a. So therefore b sin b cos cos ka. B cos k. But from previous we evaluated what is the value of b, that is equal to 0 from previous expression. Equation 5 says since b is equal to 0, the equation reduces to 0 is equal to a sin ka. So as per condition, a cannot be equal to 0. A is not equal to 0. Then possibility is sin ka is equal to 0. Product is equal to 0. So therefore sin ka is equal to 0. When exactly sin ka is equal to 0? We know that sin n pi is equal to 0. So therefore, of course, value of n is equal to 1, 2, these are called as quantum numbers. N is called as quantum numbers. So comparing equation 6 and 7, so you get n pi is equal to ka, or k is equal to n pi by a. So you got the k value. So let us substitute the value of k in equation 4. So you get psi is equal to a sin n pi by a x, or simply you can say psi n is equal to a into sin n pi by ax. Okay, because n takes different values. So task is not over. We have to evaluate a in equation 9. You don't know what exactly a. So we have to perform the normalization of this wave function. since particle is inside the box, probability of finding the particle is 1, because you can find out. So therefore we can write integral 0 to a limit, because particle is inside the box, psi n modulus whole square only along x, so therefore dx is equal to 1. So only one dimension, so there is no question of dx, dy, dz, only dx. So integral 0 to a, substituting the value of psi n, a square sine square n pi by a x dx is equal to 1. But we have sine square theta is equal to half 1 minus cos 2 theta. Let us use this and rewrite this. Integral 0 to a square half into 1 minus cos 2n pi by a x dx is equal to 1. So a square by 2 is a constant. Let us take it outside the integral. A square by 2 integral 0 to a 1 minus cos 2n pi by a x dx is equal to 1. Not necessary. Okay, it's equal to 1. So let us evaluate the integral. A square by 2 into this integral 0 to a dx minus integral 0 to a cos 2n pi by a x dx is equal to 1. So let us evaluate this. To evaluate this, we shall use the integral, that is cos n theta d theta is equal to sin n theta by n. So here same thing, let us use cos n theta. Okay, so let us use that n theta d theta. So we can call 2n pi by a as n and x as theta. Okay, all right. So therefore integral reduces to a square by 2. This integral is dx, integration is x. You have to between limit is 0 and a minus then sin n theta by n is 2n pi by a divided by n, so I will write it as a reciprocal n pi sin 2n pi by a into x between limit that's equal to 1. Okay, so evaluating the limits, a square by 2 a minus 0 minus a by 2n pi sin 2n pi a divided by a minus 0, that's equal to 1. Okay, so on simplification you will get a square by 2 to a minus a by 2n pi sin 2 n pi is equal to 1. So which means a square a divided by e2 is equal to 1, or implies a square is equal to 2 by a, or a is equal to root of 2 by a. Reason is why this is so, because sine 2n pi is equal to 0. 2n pi is equal to 0. Sine n pi is equal to 0. Sine n pi is equal to 0. Double of that, 2n pi is also is equal to 0. So you are left with only this term reduces to 0. So therefore a square a divided by 2 is equal to 1. So you got the value of a. So substituting the value of a in equation 9, you get psi n is equal to a function root of 2 by a sine n pi by a x. So this is the expression for required wave function. So this is a normalized eigenfunction. This is normalized eigenfunction for the particle inside one-dimensional box. So you know that is from equation 2, whatever we assumed, 8 pi square me divided by h square is equal to k square. So from equation 8, you can recall k is equal to n pi by a. So comparing, we get 8 pi square me divided by h square is equal to n square pi square a square. Okay, so therefore E is equal to n square h square divided by 8ma square. Question 12, where n takes value 1, 2, 3, etc. So what you observe is from equation 12, energy of the particle is discrete as n can have only integer value. In other words, the total energy of the confined particle is quantized. It cannot have continuous values. We also note that n cannot zero. N value cannot be 0. If n is equal to 0, psi n is equal to 0. Which means we can say that particle is not present inside the box. If psi n is equal to 0, particle is not present inside the box, which is not true. We have assumed that probability of finding particle inside the box is equal to 1. So that means particle has to present inside the box. So therefore n cannot take value 0. N is the lowest acceptable value for n is 1. That is 1. So corresponding energy, that is for n is equal to 1, whatever value, n value is equal to 1, corresponding energy we call it as 0 point energy. So that is for n is equal to 1, we say that is 0 point energy. So expression for, so we write it as E naught, that is h square divided by 8ma square. This is 0 point energy. So the different eigenvalues, that is n is equal to 2, 3, etc. for confined particle, that is corresponding to different excited energy state, can be written as E1 is equal to, that is n is equal to 2, so 2 square h square 8 ma square, that is nothing but 4 times of E naught. H square 8 pi ma square is nothing but E naught, so therefore 2 square, that is 4 times E naught. Similarly, E2 is equal to 3 square H square 8 ma square, that is 9 times E naught. So it is continuous like that. So you can get different eigenvalues. Okay. So these values of energies are called as eigenenergy value. So next we have to see wave function, probability density and energy levels for particle in an infinite potential. So we have to find out that, so that we will see in next video. In this video I will stop here. Thank you for watching.